Hi, this is Charles Manager. Welcome back to R for Epidemiology. In this screencast, I want to continue the discussion of risks versus rates, but frame it in from the perspective of binomial distribution versus exponential distribution, or a binomial model of disease versus an exponential model of disease. So, what then are we talking about when we talk about the risk of death versus the rate of death? Risk of death essentially is a binomially distributed outcome. It is the number of outcomes over the number of times that outcome could have occurred. But one very important distinction is that it assumes an equal period of observation for each individual in the study. That really might not be something that you can assume, particularly for diseases where people are dropping, where you're doing a cohort study and people are dropping out. On the other hand, the exponential, or an exponential, and by exponential I mean to the base e, the exponential distribution for disease outcomes, or an exponential model of disease outcomes, basically assumes a risk where we exponentiate to some sort of risk, to some sort of rate of some kind. The rate, which we've been working with in a exponential model of disease, is sometimes called lambda, and the actual exponential model of disease is 1 minus e to the minus lambda, and that's the probability distribution. If we are following folks over some period of times, we multiply by time. So it would be 1 minus e to the minus lambda times time. And in our brief little example where we talked about melanoma death with the melanoma data set we were just talking about, there were 57 deaths from melanoma in the data set. Now, if we were calculating the risk of death, the risk we said was 57 deaths over 205 people, which in this case would work out to 0.28-ish, or about a 28% risk of death. And this is the risk calculation based on the binomial assumption of equal observations. If, on the other hand, we cannot reasonably assume equal observations, we may want to consider an exponential model. As I said, it's 1 minus e to the minus lambda times t, a relatively simple formula. And in this case, we can calculate this lambda, or this rate, based on our data as the 57 outcomes over the total, I believe it was 1,240-ish total person years. And that would work out to a calculation of about 0.45, 0.045. This would be our lambda, that would be our rate. If we wanted to calculate that, we would calculate 1 minus e to the minus 0.05, give or take. I actually have that calculation up here in R. And what do I have here? Yes, actually, this is the way I have it set up here. I actually have it for a 5-year period. If we were interested, so that's the mortality rate. I just basically plucked that out from our previous calculation. If you recall, we calculated the mortality rate based on the number of deaths over person time. That's mortality rate right there. And I'm just plugging that into this little formula that I just told you about. And we could calculate that for a 5-year time period. What's the exponential risk of death over a 5-year time period? And we get the result, get this out of the way, of about 20%. I multiplied by 100 here. So there's about a 20% risk over a 5-year time period, which kind of starts approximating the full time period. Now, there is an assumption that comes with the exponential model of disease as well. And that assumption is not necessarily that there is the equal periods of observation, but that the risk, or that there's a constant hazard. And this brings us to the idea of what is actually a hazard. And you'll see reference to hazard when we start talking about survival modeling. And basically, the hazard of a disease is the probability of the disease over some time increment, from time 1 to time 1 delta, or time delta, or something like that. Now, basically, it's just the probability of disease over or given some time increment. That is the hazard. We can really interpret it as a risk or probability at most of the time at the population level. So we can consider the hazard to be about equal to a population level risk or probability. If we were interested in using an exponential model, we would have to assume that there is an equal or constant hazard over time. And we do that a lot, and we use exponential models quite often. But there's another tool available that does not constrain us to assuming this constant hazard over time. And that tool is the Kaplan-Meier survival curve and the proportional hazards model. And so in our next screencast, we will talk about the Kaplan-Meier survival curve, and then after that, proportional hazards. And please don't mind my writing. It's absolutely awful. But in the next screencast, we'll talk a little bit about Kaplan-Meier.